So what makes a technical resume really jump out at you from a stack of, I don't know, hundreds?
It's a great question. Because if you're just skimming, you see the buzzwords,
Yeah.
right? Java, Spring Boot, microservices.
Exactly. It's like you're just reading the table of contents.
Yeah,
But the real story, the actual depth that's in the projects.
it's in the projects, the results you can actually measure, and I think most importantly, it's in their ability to talk you through how things break.
How things break, yes.
Precisely. We're not looking for someone who can just recite definitions from a textbook. We're looking for someone who's actually felt the heat.
Right. Someone who's been there at 3 in the morning when a system fails and knows exactly which tool to grab.
Yeah, a developer who's only ever built, let's say, simple CRU'd applications, they just don't speak the same architectural language as someone who's had to manage distributed transactions across 10 microservices at peak load. It's a whole different ballgame.
And that is exactly our mission for this deep dive. We're going to dig into a very specific and I think very rich source, the CV of a Java full-stack developer. His name is Nabil Hussein Akhtar.
And we're going to use this profile, which details, what is it, about 3.3 years of experience?
Yeah, 3.3 plus. And we're using it as a blueprint to sort of reverse engineer what interview success looks like at this level.
So for you, the listener, this is really a shortcut.
It is. We're going to look at his main project, a high-traffic travel and hotel booking platform. It's actually for lastminute.com, which, I mean, that name alone implies massive scale and complexity.
Oh, absolutely.
And from that, we're going to figure out the 5 most critical scenario-based questions that an expert interviewer would, well, they'd have to ask to confirm he's the real deal.
Yeah, we are moving so far beyond what is Spring Boot. We're getting into questions like, describe the trade-offs of using Saga choreography versus orchestration in your booking flow.
And those are the kinds of insights that separate developers who can, just follow instructions from the engineers who can actually design and own production systems.
Let's do it.
Okay, let's unpack this profile. We'll start with section 1. The core technical identity. This is, the initial screen, the tell me about yourself part, but a much deeper version.
The foundation.
Exactly, where we establish the foundation and confirm that baseline expertise.
All right, so looking at the summary here, the profile sets the domain pretty clearly. Java full-stack developer, 3.3 years of experience, and a focus on scalable, secure enterprise applications.
And that little logistical detail, immediate joiner, that's there. But what really matters to us is that core stack confirmation.
Right, and the first thing that just jumps out at me is the Java versions listed. Not just one, it's Java 8 through 17.
That is not a trivial range. I mean, Java 8 was this foundational shift. It introduced functional programming with Lambdas and the Stream API.
A total paradigm shift for many Java developers at the time. For sure. And so a developer who started there and has successfully migrated or even built new applications using Java 17, they've had to master 2 pretty distinct paradigms of the language.
I think that's such a critical distinction to make. It is one thing to, write some basic Java 17 syntax.
Of course.
But a truly experienced developer, they know the pain points. They know the migration headaches.
Yeah.
The move from 8 to 17 that involved learning the module system, record types, understanding huge changes in garbage collection.
Exactly. And if they haven't really mastered those transitions, any large-scale enterprise build they do is going to be, well, either bloated or just really inefficient.
They didn't understand performance tuning across 2 different eras of the JVM architecture.
And right away, you see this jump into the big enterprise tools. AWS, Kafka, Docker, Kubernetes, CI/CD.
Yeah.
That immediately tells an interviewer that this candidate isn't just coding isolated features in a little silo. They've been exposed to the entire production-grade lifecycle, and they're working in an agile Scrum environment.
That full-stack exposure all the way through to deployment and orchestration, that is the first major signal that just raises the bar for the interview.
It really does.
When I see Kubernetes listed, I know I can just skip the basic questions about deployment scripts. I can go straight to asking about, say, service mesh complexity or auto-scaling strategies in a live production cluster.
This profile implies a deep, critical understanding of that whole infrastructure layer that supports their application code.
Which lets us drill down into their essential tooling mastery, specifically on the back end.
Right, the back-end depth. Spring Boot and microservices, okay, that's expected. But seeing Spring, Cloud, and Hibernate listed, that's where you find the gold.
Okay, let's focus on Hibernate first. Listing Hibernate means they have ORM, object relational mapping, expertise. But ORMMs, while they're convenient, they're often where junior developers accidentally introduce just massive performance bottlenecks.
That is the key challenge. ORMs abstract away the SQL, which is wonderful, until you run headfirst into the infamous n+1 select problem.
Yeah.
It happens when Hibernate fetches a list of parent entities, let's say 100 hotel bookings,
Okay.
and then it executes 100 separate, totally non-optimized SQL queries to get the related child data, like the user details for each booking.
100 separate queries. You can just see the database grinding to a halt.
It brings the database to its knees during peak traffic. So a candidate who lists Hibernate, they must know how to explicitly configure fetching strategies. Lazy loading, eager loading, using things like join fsh or batching to avoid that exact scenario.
So just by listing that one tool, they're implying they know about data access optimization in a real live production environment.
They have to.
Okay, moving on to the microservices architecture. They list Spring Cloud. That's a big umbrella framework that handles all the common infrastructure concerns of microservices, right?
Yes, Spring Cloud signals mastery of those key orchestration components. Things like service discovery, how do services even find each other in a dynamic environment?
And configuration management.
Configuration management, exactly. How do you manage environment-specific variables across 10 different services without going insane?
And client-side load balancing.
That too. And that ties directly into the next detail here, the mention of Feign client.
Which is a key detail for efficient and, I guess, maintainable communication between services.
It's vital. Feign client is a declarative REST client. So instead of writing all this verbose REST template or web client boilerplate code for service-to-service calls,
You just define an interface.
you just define a SQL Java interface.
Right.
And Feign handles all the complexity of making the HTTP call, including the integration with client-side load balancing, and critically, the integration with circuit breakers for failure handling, which I'm sure we'll get into.
We will.
Seeing Feign on a CV tells me they are proficient in efficient and resilient internal communication within that Spring ecosystem.
Okay, so let's switch gears to the front-end breadth, because this is a full-stack developer.
Yeah.
The CV lists both React.js and Vue.js.
Right.
And this just opens up a perfect scenario question, one that tests high-level decision-making and business awareness, not just, their ability to write JSX or some templates.
This is a classic architectural maturity test. You want to know why they would choose one technology over the other for a massive enterprise platform like lastminute.com?
Not just how they coded a component in it.
Exactly.
All right, so here's the scenario question I'd ask based on this. If you had to choose between React and Vue for building the new high-traffic user interface for the lastminute.com booking flow, specifically the search result and the hotel detail pages, what specific factors, based on your experience at this scale, would guide that decision? And more specifically, why did you opt for a modern single-page application, an SPA framework, instead of more traditional server-side template engine like Timeleaf or JSPs?
Great question. The initial part of the answer has to immediately dismiss the server-side engines for a system that needs a 45% load time reduction.
Right, that's a non-starter.
Those engines, like Timeleaf, they require a full page refresh or a server round trip for every little state change or filter application. They just cannot provide that interactive, dynamic, fast user experience that a consumer expects today when they're filtering search results in real time.
The performance gains would be minimal, and the user experience would feel, archaic.
Totally.
Agreed. So the choice of React versus Vue is more nuanced, though. What does an expert candidate analyze there?
Well, the choice usually hinges on factors that go way beyond just technical elegance. You have to think about ecosystem size, the talent pool, and long-term maintainability.
Right. Business-driven trade-offs.
React, being backed by Meta and having this massive global community, offers an enormous ecosystem of libraries, support tools, and most importantly, talent.
The hiring pipeline.
For a large enterprise platform like lastminute.com, recruiting developers who already know React is just easier, faster, and often cheaper than recruiting for a smaller ecosystem like Vue.
That makes sense. Vue is often praised for its simplicity, though, right? A gentler learning curve, less boilerplate for certain things. Does that benefit ever outweigh the talent pool concern?
For, say, rapid internal tools or smaller projects, Vue often wins on pure development speed. But for a mission-critical, high-traffic system that needs long-term maintainability, extensive and mature third-party integrations.
Like complex map libraries or?
Exactly, or internationalization frameworks, advanced state management like Redux or Zoostand. React's vast and proven stability usually makes it the safer, more scalable, and frankly, less risky choice for an enterprise.
So a superior answer would acknowledge Vue's benefits, but ultimately prioritize React for that organizational stability and the external resources.
That shows they're thinking like a lead or an architect, not just a coder.
Okay, and finally, in this foundational section, we've got database expertise. They've listed relational, like MySQL and PostgreSQL, and NoSQL MongoDB, Redis cache plus ER diagrams.
The fact that they list this variety implies they understand the concept of polyglot persistence.
Meaning they know that not every data problem is a nail for the same relational hammer.
Relational databases are crucial for high-integrity, AC-compliant transactions. Think booking, payment.
The really critical stuff.
Right. But NoSQL, like MongoDB, is much better suited for flexible schemaless data like customer reviews or user profiles. And Redis cache, it's all about speed, which we'll definitely get to.
So they understand when to trade off that strict relational integrity for speed and flexibility.
Which sets the table perfectly. We're dealing with someone who's seen how all these disparate systems have to work together at scale, an architect in training.
Let's move to where the real complexity lies then. Section 2.
Building resilient distributed systems.
Exactly. The key project here is that high-stakes travel and hotel booking platform. It involves, 10-plus distinct microservices? User, hotel, inventory, booking, payment, search, reviews, notification.
Right away, an interviewer knows they're dealing with distributed complexity, huge concurrency challenges, and a very high risk of cascading failures if the architecture isn't just rock solid.
And that scale forces you into very specific, sophisticated solutions.
Namely, event-driven architecture and decentralized transaction management.
Let's start with 2.1, event-driven architecture. The source specifically says the candidate, and I'm quoting here, designed event-driven workflows using Kafka for booking confirmations, cancellations, and inventory sync.
Okay, so inventory synchronization on a travel platform is the classic high concurrency challenge.
For sure.
When two users at the exact same moment hit book, you absolutely must ensure that the last available room is only sold once, and you have to do it without locking the entire database, which would just cripple performance for everyone else.
So why is Kafka the right tool here? Why does it solve this better than just making synchronous API calls between the services?
Kafka solves two big problems. First, decoupled communication. The booking service doesn't have to wait for the inventory service to respond and confirm the room is reserved. It just sends an event into Kafka and moves on.
Which improves the overall system responsiveness for the user.
Massively. And second, Kafka provides an ordered, durable log. This log is critical because if an inventory service goes down for a few minutes,
The events just queue up safely.
the events queue up safely in Kafka, and when that service restarts, it picks up exactly where it left off, processing the events in the correct, guaranteed order.
Decoupling is powerful, but it introduces a massive risk, eventual consistency. If a consumer fails to process a critical event, let's say a cancellation event, that room could stay unavailable forever. That's a direct financial loss for the company.
Great.
So how do you handle that kind of operational failure gracefully?
And that leads us immediately to the first critical scenario question. This one tests their understanding of Kafka's operational resilience and the absolute need for what are called idempotent consumers.
Okay, let's hear it.
Scenario question 1, data integrity and event failure. You mentioned using Kafka for inventory synchronization, which relies on eventual consistency. Describe a detailed, step-by-step scenario where a critical consumer fails to process a booking cancellation event due to a temporary database connection error. How did your design, relying on the idempotency principle and related tools like Spring Retry or Dead Letter Queues, ensure that the inventory eventually received the update and that you prevented phantom bookings or overselling?
Okay, so the candidate has to tackle 3 layers there. The immediate retry, the core logic, which is idempotency, and then the long-term failure mechanism, the DLQ.
Absolutely. So let's start with idempotency. In a system like Kafka, messages can sometimes be delivered more than once. It happens, especially if a consumer commits its offset before it successfully processes the event and then it crashes.
Right, so it thinks it's done, but it hasn't actually finished the work.
Exactly. So an idempotent consumer has to be designed so that receiving the same booking cancellation event 5 times yields the exact same result as receiving it just once.
Which is, the inventory count for that room increases by 1.
Right. If the system is not idempotent and that message gets reprocessed, the inventory count could mistakenly increase by 5, which leads to overselling or these phantom rooms that don't actually exist.
So how do you enforce that idempotency in the code?
Typically, you embed a unique transaction ID or an event ID, sometimes called a JTI or a correlation ID, right inside the event payload.
Ah,
So before the inventory service updates its database, it first checks the dedicated tracking table or maybe a Redis cache. If that specific event ID has already been processed, it just acknowledges the message and moves on without executing the update logic again.
okay, that makes sense. So what about that short-term retry failure, like a momentary network glitch?
Well, most modern Spring Kafka consumers have a built-in retry mechanism. Often it leverages something like a Spring retry back-off strategy.
So it tries again after a short delay.
It tries again with an increasing delay, say 1 second, then 5 seconds, then 10 seconds. This ensures that a temporary transient error, like a 5-second database timeout, doesn't kill the whole transaction.
But what if the database is down for hours? This moves from a transient error to a persistent structural failure.
And that's where the dead letter queue, the DL is absolutely mandatory. After a defined number of failed attempts, say 5 or 10 times,
The system has to give up.
it has to stop trying to process that message. Instead, it reroutes the failed message to a designated DLQ topic in Kafka. This is so crucial because it isolates the problematic message.
It prevents the consumer from getting stuck, which is called head-of-line blocking.
Right. And it allows the main service to continue processing all the new healthy events that are coming in. A top-tier candidate would then mention that this DLQ is constantly being monitored by a dedicated service or an alerting tool like PagerDuty.
Flagging those messages for immediate human review and fixing.
Yep. The depth proves they've actually operationalized Kafka resilience. They've seen it fail in production.
Okay, that's a great answer. Let's move to 2.2. Distributed transactions and failure handling. The CB says they implemented Saga patterns and circuit breakers for resilient distributed transaction handling.
The inclusion of Saga patterns, that immediately elevates the entire profile. This is the sophisticated, modern replacement for the old, centralized two-phase commit or 2PC in a microservices world.
And we established that 2PC is basically out because it creates a synchronous blocking lock across all the services involved in a transaction.
Right. Sagas manage that same complexity by using a sequence of local transactions and then, critically, compensation actions to undo them.
But there are two main Saga patterns, aren't there? Choreography and orchestration. In a system with 10 services like this one, which is more likely.
That is the nuance we need to explore. So choreography is fully decentralized. Each local transaction just publishes an event that triggers the next service in the chain.
It's very loosely coupled, which sounds good.
It is, and it's resilient. But debugging a failing transaction that spans 10 different event hops, it's notoriously difficult because there's no single control point. You're just chasing events through logs.
So what's the alternative?
Orchestration. This uses a central coordinating service, the Saga orchestrator, that explicitly dictates the steps and handles all the compensation logic. It's a central brain for the transaction.
Okay, so given the scale of lastminute.com and the need for, rigorous auditing in financial transactions, orchestration seems like it would provide better visibility and easier compensation management.
I agree. Even though it does introduce a single point of coordination complexity, it's often the better choice for something this critical.
And an expert developer would have had to make that choice consciously.
For sure. Which leads us perfectly into our second scenario question.
Let's hear it. Scenario question 2. Failure mitigation and compensation. Explain the full workflow for a failed payment service within a Saga pattern during a hotel booking. Specifically, detail step by step how the compensation actions roll back the changes made by the inventory and notification services that were successfully completed before the payment failed. And then, why did you choose the Saga pattern over a two-phase commit in this high-traffic context?
Okay, so the answer has to clearly map out both the forward flow and the compensation flow.
The happy path and the sad path.
Exactly. So forward flow. 1, the user requests a booking. 2, the booking service creates a local pending record and triggers the next step. 3, the inventory service gets the event and executes its own local transaction to reserve the room. 4, the notification service sends a booking is pending payment email.
And then step 5.
The payment service attempts to charge the user's card, and it fails.
So that failure event has to be broadcast or somehow communicated back to the orchestrator.
Correct. The payment service, when it fails, emits a payment failed event. This event then triggers the compensation actions in reverse order.
So first, the inventory service.
First, the inventory service subscribes to that failure event or is told by the orchestrator, and it executes a compensation transaction, which is to release that specific reserve room back into the available inventory.
And then the notification service has to send another update.
Right. It's triggered to send a second update to the user saying, your booking failed due to payment issues. Please try again.
The critical realization here for the interviewer is that compensation is not a true ACID rollback. It's not magic.
It's not. It's a new, intentional, local transaction that's designed to undo the business effect of the preceding successful steps.
And it requires careful design because the compensation action itself has to be idempotent and reliable too. It could also fail.
Exactly. And the rationale for sagas over 2PC, it all boils down to availability and scalability. You are trading some transactional complexity for high system availability.
Because 2PC is synchronous and it blocks the whole transaction path.
Well, sagas are asynchronous and loosely coupled. That means one service going slow doesn't necessarily block the entire system, which is essential for surviving peak booking periods.
Okay, but I have to challenge this point a little. Sagas are notoriously difficult to debug, right? Especially choreography-based sagas that rely just on these implicit events.
That's a very sharp point.
Doesn't that inherent complexity and failure recovery sometimes negate the availability benefit? Especially when you have some unknown production bug at 2 in the morning.
It's a fair challenge, and the sophisticated answer has to address observability, which links us directly to Section 3.
Oh.
Yes, the logic is complex, but that is precisely why the CV lists Zipkin. Distributed tracing is the mandatory countermeasure for saga complexity.
You can't trace an asynchronous saga using traditional logs. It's impossible.
It's a nightmare. Zipkin allows you to see that entire chain of events, the forward flow and the compensation flow, all linked by a single trace ID. It transforms an impossible debugging task into a manageable waterfall visualization.
That closes the loop very elegantly. Okay, the source also mentions the use of circuit breakers. This is like the last line of defense against those catastrophic cascading failures.
And it connects directly to the sagas and the Fein clients we talked about. If one of the 10 services, let's say the reviews service, starts returning 500 errors because of a database bottleneck,
right,
the circuit breaker pattern will trip. Instead of the booking service waiting indefinitely for the failing review service and thereby exhausting its own thread pool,
the circuit opens.
The circuit breaker opens and it immediately returns a fast fallback response. Maybe an empty list of reviews or a cached copy. It protects the entire system from collapsing. It's the bulkheading principle in action.
Absolutely essential. Okay, finally for this section, 2.3, security and access control. The candidate secured modules using Spring Security plus JWT with RBAC and token validation.
RBAC, role-based access control, that's pretty standard practice. But implementing JWT, or JSON Web Token, validation across 10-plus distributed microservices. That's where the real architectural challenge lies, specifically around managing state.
Right, because the core benefit of JWTs is that they're stateless. Once the authentication service issues the token, any other service booking, inventory, payment can validate the signature locally without constantly phoning home to a central authority.
And that scales beautifully.
Right.
But that statelessness is also its Achilles heel for immediate security needs. If a user logs out, or if an admin forces a session termination because of suspicious activity, how do you instantly tell all 10 of those microservices to stop trusting that token?
You can't just wait for the token to expire, especially if you have a long expiry time for a better user experience. That would be a massive security loophole.
This is a textbook security architecture challenge, and it leads directly to our third scenario question. Scenario question 3. Security and stateless revocation. In a distributed microservices setup using JWTs, the core benefit is statelessness, allowing for fast, local token validation. However, how did you handle instant token revocation if a user session needed to be terminated early? Detail the specific architectural trade-offs of your chosen method, linking back to your listed skills like Redis cache, which is necessary for this kind of solution.
So the candidate has to admit that perfect stateless security is often an illusion in these systems. They had to reintroduce a minimal amount of centralized state to solve this.
The best practice answer integrates their Redis cache skill. Since the cryptographic signature check is already super fast, like the bottleneck isn't the validation itself, it's forcing a revocation check.
So they would describe maintaining a distributed JWT blacklist.
A distributed JWT blacklist, or a revocation list, stored in Redis. So every time a service gets a JWT, it performs two very fast checks.
One is the signature.
One, cryptographic signature validation, that's stateless, guarantees integrity. And two, a lightning-fast lookup in Redis to see if the unique token ID, the JTI claim, is present in that blacklist.
And if that JTI is in the
The
blacklist,
token is rejected instantly, regardless of its original expiry time.
using Redis is so essential here because the performance impact of that state check has to be negligible. I mean, if that lookup adds 50 milliseconds of latency, you've basically negated the whole performance benefit of using JWTs in the first place.
Exactly. Redis, being an in-memory data store, minimizes that latency to ensure you gain that security control without sacrificing speed. It's a perfect example of trading off a tiny fraction of pure statelessness to achieve real-world operational security.
It shows architectural maturity, a holistic view of the system's requirements, performance, security, and maintenance.
Yep.
Right. Moving into Section 3, we're now looking at optimization. How a candidate took this resilient multi-service architecture and made it fast enough to handle high traffic. This is where we see the impact on the bottom line.
And the first quantifiable achievement here is the most persuasive one. 3.1, high-demand caching. The candidate implemented caching for high-demand endpoints using Redis, reducing load time by 45%.
Wow. That 45% reduction is not just a technical win. That translates directly into revenue and customer satisfaction. Where would this be implemented on a booking site?
Well, it would be implemented at the points of highest contention and least volatility. So specifically, search result pages, hotel listing details, and maybe pricing aggregations that only refresh every few minutes.
And caching those results reduces the load on the back-end microservices.
And the networking infrastructure, and crucially, the primary transactional databases, the PostgreSQL or MySQL instances.
We know Redis is used, but the critical challenge in caching is always managing the content. The customer must not see a cached result that shows a room's available when it was actually booked 2 seconds ago.
That's the speed versus freshness trade-off.
Which creates our fourth scenario question, focusing entirely on those cache management policies.
Right. Scenario question 4, cache management and consistency. You achieved a 45% load time reduction using Redis. Describe a situation where stale data in the cache caused a critical customer-facing issue, like a ghost booking, where an available room was shown but then failed immediately upon checkout. How did you design your time to live, your TTL policies, your cache update strategies, or your active invalidation mechanisms to mitigate this trade-off between speed and freshness, especially for that sensitive inventory data?
The junior candidate might just talk about a generic TTL. We set it to 5 minutes, but an expert needs to discuss differentiated policies based on how sensitive the data is.
Exactly. For static data, like the hotel description or its address, a long TTL is fine, maybe 24 hours. For semi-dynamic data, like average user ratings, maybe an hour is okay.
But for that volatile inventory critical data, a long TTL is a disaster.
For that, you must use active invalidation.
So let's connect this back to our other architectural components. How does active invalidation work in this distributed context?
The most sophisticated answer links this right back to Kafka, closing that whole architecture loop.
Ah, nice.
The inventory service, immediately after it successfully processes a new booking or a cancellation event, which updates the relational database, the source of truth, it must proactively send a specific invalidation message into another Kafka topic.
And that message is consumed by the caching service.
Right, which immediately executes the DEL command for that specific key in Redis, invalidating that cached inventory item.
So instead of just passively waiting for the TTL to expire, the system is actively yelling at the cache that the source of truth has changed.
That's a great way to put it. It ensures maximum freshness for the most sensitive data points, preventing those ghost bookings. It's the difference between passive and active consistency management.
They'd also have to detail the strategy they use, like cache aside, right?
Likely cache aside, where the application service checks Redis first. If it's a miss, it hits the database and then writes the result back to Redis for next time. But the critical part is ensuring that invalidation mechanism is robust.
Got it. Moving on to 3.2, search and advanced data structures. The CV says they created elastic search-powered search engine with filters for price, rating, amenities, and location.
This confirms that the candidate understands the limitations of relational databases for complex high-speed searching. Simple SQL-like queries are just not scalable when you have millions of hotel listings with multiple faceted filters.
It doesn't work.
Elasticsearch shows expertise in things like inverted indexing, relevant scoring, and scaling non-relational search. Handling a query like, find me hotels near the Eiffel Tower that are 4-star, have a pool, and are sorted by price,
That requires advanced geospatial indexing and faceted navigation.
which are Elasticsearch specialties. This detail also implies a complex data pipeline that has to synchronize the relational data, the source of truth from MySQL, into the highly optimized document structure that Elasticsearch needs.
That sync process itself is a major engineering effort.
And don't forget the ranking algorithms. The candidate had to design custom relevant scoring. How do you make a hotel with a 5-star rating show up higher than a 3-star, even if the price is similar?
That's where engineering meets the business logic.
It's moving beyond simple filtering to true information retrieval mastery.
Okay, finally, 3.3. Distributed observability. This is so vital in a microservices environment with complex sagas and Kafka event streams. The candidate lists Zipkin, the ELK stack Elasticsearch, Logstash, Kibana, and structured logging with SLF4j.
If you are running 10 microservices, you are operating completely in the dark without this stack. And listing Zipkin specifically indicates knowledge of distributed tracing.
The ability to inject and track a single request ID across the entire system, from the API gateway through the booking service, the inventory service, all the way down to the payment service.
Without tracing, when a user reports latency, you're stuck looking at 10 different uncoordinated log files, trying to piece together the sequence of events like a detective.
With tracing, you get a clean visual waterfall diagram showing which service spent the most time processing that request.
Which is the perfect setup for our fifth and final architectural scenario question, a high-pressure production debugging emergency.
Let's do it. Scenario question 5. Production debugging and isolation. It's 2 a.m., and the on-call monitor is reporting high latency above the 99th percentile, specifically in the notification service endpoint. But the upstream booking service is reporting normal operational health. How do you use Zipkin and the ELK stack, specifically your structured logs viewed via Kibana, to rapidly isolate whether the bottleneck is network latency, a slow database query in the downstream service, internal thread contention, or maybe an issue with an external integration like Twilio or SendGrid?
Okay, the candidate must describe a disciplined, systematic triage process using these specific tools. They have to show they know how to separate internal resource issues from external API issues.
So that's step 1.
Step 1. Immediate log analysis in ELK or Kibana. They have to start with Kibana, filtering the structured logs for the notification service during that latency window.
And structured logging is key here.
It's everything. Instead of searching messy plain text, they can filter directly on metadata fields like latencyms or DB query time. They should be looking for immediate high error rates or logs that show specific database query times that suddenly spiked.
And if the issue isn't obvious in the logs. So the SQL queries look normal. Where do they go next?
Step 2. Distributed tracing in Zipkin. They move to the Zipkin interface. They search for traces that are exceeding the latency threshold for the notification service. The trace will show the total duration, but the real power is in the subspans.
Breaking down the internal operations.
The candidate should explain that Zipkin breaks down the internal operations of that service, time spent communicating with its database, time spent performing internal Java logic in the application code, and critically, the time spent making external API calls to downstream services like Twilio.
So if the span labeled external API call to Twilio is consuming, say, 90% of the total request time, the problem is immediately identified as external.
Right, and the engineering team can pivot to contacting the third-party provider instead of wasting precious minutes debugging their own application code.
And conversely, if the span for the internal database call is unusually high, they know they have a slow query or an indexing issue.
Or if the internal logic span is spiking, it points toward resource exhaustion, like thread contention or garbage collection pauses. This is the difference between blindly restarting a service and confidently identifying the root cause within minutes.
That is the definition of production-grade expertise.
It is.
Okay, our final section, section 4, focuses on the non-functional requirements, how the code actually gets deployed, how it runs, and how the cloud is leveraged. This confirms the full stack title extends right through to infrastructure as code and DevOps.
And the tools listed here confirm a mastery of modern CI/CD.
Let's look at 4.1, the power of automation. They built CI/CD pipelines with Jenkins and GitHub Actions for automated deployments.
Using both of those tools suggests a couple of important things. First, versatility. Second, and this is often more revealing, they've likely had to manage a complex migration or run a hybrid environment.
Moving from an older system like Jenkins to a more modern cloud-native one like GitHub Actions.
Right, which implies serious proficiency in pipeline scripting, Groovy for Jenkins, YAML for Actions, and deep familiarity with different deployment targets like Kubernetes.
And automated deployments are the backbone of frequent, safe, repeatable releases. Without this, trying to maintain 10 microservices would just be a manual deployment nightmare.
For sure. Then moving to 4.2, cloud services integration on AWS. They list the foundations, EC2, S3, RDS, Lambda, but the real insight is in the project detail. Integrated AWS S3 presigned URLs for secure, optimized image uploads.
This is such a small but brilliant detail that reveals practical, cost-effective, and secure cloud engineering. Let's break down the traditional, less efficient way of handling a hotel image upload versus using a presigned URL.
Okay, so in the traditional way, a user uploads a high-resolution image to your application server, the booking microservice. That application server then has to dedicate CPU, memory, and network bandwidth to validating the file, streaming the potentially huge file, and then uploading it to S3.
And that process can easily block application threads, increasing latency for your critical business logic.
Exactly. A presigned URL architecture is fundamentally different. Your lightweight microservice only authenticates the user, generates a temporary, short-lived URL with permission to write to a specific S3 bucket path.
And then it passes that URL directly to the client's browser.
And the client then uploads the image directly to S3, bypassing your server entirely for the heavy lifting.
The benefits are enormous. It hits 3 key areas. Performance, because your app server is unburdened. Scalability, because S3 is designed to handle massive concurrent uploads far better than any EC2 instance.
And security. The client never sees your permanent, long-term AWS credentials. They only have a temporary, signed permission ticket. This is a sign of a developer who thinks about performance at the infrastructure and cost level.
It's an architectural decision that saves money on compute resources and improves responsiveness for the user.
Absolutely.
Okay, and finally, 4.3, system maintenance and reliability. The candidate developed automated cron jobs for price updates, inventory refresh, and stale booking cleanup.
This detail reminds us that production systems are living things. They require proactive, robust maintenance, and that stale booking cleanup is a direct necessity imposed by the distributed transaction management we discussed earlier with sagas.
Right. If a saga fails partway through, it can leave a booking record in a transient or pending state that the compensation action never fully resolved. Those records become orphaned.
And the cron job is the safety net. It's the background process that sweeps up these abandoned records after a defined grace period, say 12 or 24 hours.
It deletes the partially reserved inventory and marks the booking record as permanently failed,
ensuring long-term data consistency and freeing up inventory that might have been accidentally locked by a partial failure.
And crucially, the system for running these jobs has to be resilient too. A sophisticated architecture wouldn't just rely on a single server's built-in cron scheduler.
No way. They would have containerized it via Kubernetes or leveraged the AWS Lambda skill they listed, ensuring the job is reliable, auditable, and scalable without needing a dedicated always-on EC2 instance.
So the entire profile, when you scrutinize it through these scenario questions, it's not a list of disconnected skills.
Not at all. It's a diagram of a highly resilient, cost-optimized, and modern distributed system that's capable of handling high-stakes financial transactions under pressure. That is what an expert interviewer is looking for.
This has been an incredibly deep look into what 3.3 years of high-quality experience really looks like in the Java full-stack world. We've shown how you can move past simple syntax checks and really anticipate, analyze, and answer these complex architectural scenario questions that test operational readiness.
The key takeaway, I think, is pretty clear. A strong full-stack profile needs to move beyond just basic functionality or standard CRU'd app and demonstrate mastery in 3 interconnected high-leverage areas.
Okay, what are they?
First, resilient distributed architecture. That means using Kafka for eventing and sagas or circuit breakers for failure handling. Second, performance optimization, leveraging Redis for speed and Elasticsearch for scalable search. And third, production-grade deployment and observability. That's your CI/CD automation, distributed tracing with Zipton, and secure, cost-effective AWS integration.
And for you, the listener, understanding this kind of profile gives you a comprehensive checklist for what truly matters when you're designing or reviewing a high-scale application. And critically, it prepares you for those deep architectural questions that really define expert-level interviews.
And that leads us to our final provocative thought. We've spent a lot of time today discussing the saga pattern. It's a crucial, complex solution that was necessitated by the move from centralized, monolithic transactions to decentralized microservices.
And the most skilled developers aren't just the ones who can code the features.
They are the engineers who can design and implement the failure paths.
Right. As technology continues its march toward decentralization, becoming more and more serverless and ephemeral, where functions and resources might only exist for mere seconds.
The traditional saga pattern, which was designed for long-lived microservices, starts to face new challenges in state coordination and recovery.
So if the saga pattern was the answer to distributed transactional failure in the traditional Spring Boot microservices world,
What common architectural pattern is destined to become the next saga pattern as systems become even more ephemeral, with dozens of short-lived AWS Lambda functions all trying to coordinate state?
think about those serverless functions. They're stateless, but they still need guaranteed delivery and rollback if a subsequent function fails.
Where?
What pattern focuses on reliably writing local state changes to an event stream before committing the database transaction, ensuring atomicity in an increasingly event-driven ephemeral world? It's a key challenge to mull over as you build your next robust system.
Something to think about.
Until next time, keep digging deep.